All right, grade 11s, welcome back to math. We've got a little bit of exponential stuff left to wrap up before we move on to our finance for the last couple of days here. So here we're going to be looking at problems that involve exponential growth, and then in the next video, problems involving exponential decay. So in this first video, we're going to be using exponential functions to model and solve problems involving exponential growth. Okay, so here, this corresponds with your handout, which you may have printed or you might just want to look at on your screen. But it says in 1978, researchers placed a group of 20 deer on a large island in the middle of a lake. The deer had no natural predators on the island. Researchers collected population data and created a graphical model. So that's what we're looking at in this graph here, the deer population on an island. It says it started in 1978. So that's what this axis label is referring to, how much time has passed since then in years. And then the y-axis is the number of deer, starting at 20, just like it says in that little blurb of text, and growing from there over time. An extra little piece of information here, researchers estimated that the island had enough resources to support 320 deer. So this graph goes as far as 28 years after 1978, and the population of deer was up around 220, 225 maybe, so a little bit over 220. And the question that we're going to be answering is, in what year will the deer population be too large for the island? So really, when is it hitting 320 or higher? So here we have a graph to work with, which makes things a lot easier. We have two options. We can extrapolate the curve on the graph. So this is a word you might have seen in grade 9 with linear relations, extrapolation. And we can also use a table of values to spot the pattern and see if we can just hit that number 320. Okay, so I'm going to advance to another slide just because this one's getting busy. And we're going to try both of those two things. So I've added a horizontal line here just so we can kind of see it a little clearer at 320. So that's our target. And strategy number 1, I'm just going to try extrapolating the curve. So it looks like it's this nice smooth growth. I'm just going to extend it. So this is not perfect by any means, but assuming there's no major changes that happen, that's roughly the trend that the deer population should follow. Okay, so I've tried that out. Based on my very rough curve, we can look at 320 deer. Looks like it's happening at maybe 31 or 32 years, just with a really rough sketch. So maybe 32-ish. That's not very accurate, so we can also use the table of values to do a little bit better than that. So I started setting one up over in the corner of the slide. And what I'm going to do is pull some of the nice data points. So I'm not going to use every point because some of them I'd be guessing the values, but I do know for sure that 0 years after 1978, or in that year, there were 20 deer. And I can start working my way along the graph, saying after 2 years, there was a little bit more than 20. After 4 years, there's a little bit more again, but I don't really know what that amount is. It's 30-ish, but I would be guessing because it's not falling on an intersection of grid lines, like the crosshairs. That would be a nicer point for me to find. So I'm going to keep going, and over at 8 years is the first time the curve hits like a nice point again. So 8 years later, the population is 40 deer. So I'm going to keep tracing along. Looking for another one of those like nice points. Nice point. Nice because it's right on the crosshairs. So not so good, not so good. Oh, there's another good one. Okay, so some of these 12 years, it would be just a little bit less than 60, but I don't know exactly how much. But at 16 years, it's right at 80. All right, so this looks like every 8 years, we're at another nice point. That one has 160 deer. And I can see that we are now following a pretty clear pattern. So I'm going to go 8 years later, which is 4 grid lines. 1, 2, 3, 4. And I'm going to look for that point, which I had extrapolated before with the red curve. But using my table of values, adding 8 years each time, doubling the population of deer each time, I can use that pattern and with pretty good confidence say that after 32 years, the population will be hitting 320 deer. Okay, so my red like sketch on the curve was pretty close. The table of values makes that even more believable. All right, so we could say a little summary statement there. Oh, that font's going to be huge. We could say in 32 years, the population of deer will reach 320. After that, the population of deer will be too high for the island to support. Okay, and all of that came from the little blurb at the beginning, that bit of text, and a graph with a couple of nice data points on it. All right, so exponential growth. Here it looks like we were doubling the population in a consistent amount of time, every 8 years. Right, so there's our first exponential growth problem. And we're going to look at just 2 more. This one, we've got another kind of environmental theme. This one says algae in a pond grow at a rate of 10% per week. Currently, the algae cover 1/4 of the pond. An algebraic model of this situation is given by C at W. So there's some function notation similar to what you did early on in your course. Oh, that highlighter did not work. So function notation, where C is the percent covered. So C stands for covered. Maybe I'll just do it here. C is for covered after W weeks. Okay, and there's a formula to follow, and that's the algebraic model is the formula. It has a 0.25 in brackets, 1 plus 0.1, and the exponent here is W. So we're just going to kind of break that formula into its parts and figure out, well, how do you make one of these equations? When this question is given to you, and other questions, you're going to be coming up with the equation on your own, or the model on your own. So explain what 0.25 represents in this equation. 0.25, that sounds an awful lot like 1/4. So using some clever thinking, we can connect those 2 things together. And we can say, I'm going to type this, I think. we can say that 0.25 is the amount of 100% of the pond initially covered by algae. I've put initially in caps there because that's kind of the important part. That's like the starting value. And that's important because it's like the multiplier in front of the bracket. It's the amount that we're starting with. And we're going to be able to use that kind of as a rule moving forward, that whatever that multiplier in the front is our initial value, our starting value. For question B, it says explain what the 0.1 represents in this equation. So the 0.1, maybe I'll switch colors there. The 0.1 is in this spot. Inside the bracket, it's being added to 1. And looking back at like the rest of the question, the text, the only other number there is 10%. So algae in a pond grow at a rate of 10% per week. And 0.1 is the decimal version of 10%. Okay, so I'm seeing a connection between those two numbers. So again, I'm going to type this one so it's a little bit tidier. 0.1 is the growth rate for the algae, written in decimal form. I think so it was linked with the 10% given in the question. The other part of that bracket, so this is not actually what, this wasn't in the question, but I'm going to add it here anyway. The number 1 added at the beginning, we'll talk about this on the next slide anyway. But this is what it means it's going to grow. We're in the bracket ending up with a number bigger than 1. So we're multiplying by a base in the power that is bigger than 1. So this would be 1.1 times 1.1 times 1.1. And because we're multiplying by a number greater than 1, that's growth. So this is greater than 1, therefore growth is going to happen. In our second video, we're going to see a subtraction there instead. So we'll be starting with 1 and taking something away from it. So we're always going to have numbers smaller than 1, like a half, a quarter, a third, as the base of the power, which ends up leading to multiplying by a fraction again and again, and making a graph that shows decay instead. All right, our last question here, determine how much of the pond, we can round to the nearest percent, will be covered 10 weeks from now. So this one we're going to do a calculation. And we're going to calculate the amount covered, C, after 10 weeks. So I'm replacing W in the formula with 10. So I'm looking up at the formula in the question. 1 plus 0.1, and the exponent W is now going to be the number 10. Okay, so this can be simplified for sure. We can add together the numbers in the brackets to get 1.1. And now we can grab a calculator to solve this one, but I do want to be careful to follow BEDMAS, order of operations, and evaluate the exponent part of this question first, 1.1 to the exponent 10. Find that answer and multiply it by 0.25. Let's see. So I'm going to write down a partial step, which you don't have to do, but I'm doing it here anyway. 1.1 to the exponent 10 is 2.59374,246. And if I multiply those together, I'm going to get approximately 0.648. And I can use that to answer the question in percent form again. And therefore, 64.8%. Oh, it said to round to the nearest percent, so I'll round it up to 65. Approximately 65% is covered by algae. In 10 weeks. Okay, so there's another full question, like a problem solving involving growth. This one we were given, not a graph, but we were given the formula to work with. So we just kind of had to plug something in there. All right, our very last question we'll do after looking at kind of the general form of exponential growth formulas. And this kind of gives us the rule or the pattern to follow. So if you know the initial amount and the growth rate, the exponential function p at n equals, this is called p naught. I'm going to p naught. Can be used as a model. All right, so here again we have 1 plus a number. The r in that equation is the rate of growth written as a decimal. The p naught is like the initial amount or the starting value. P at n is that same quantity, whatever it happens to be. And the last one, it was the amount covered. This could be anything that's growing, like a population or something like that, depending on how many times it has grown. All right, so the number of growth periods is n. Our function depends on that, and that shows up in the exponent. So we're going to use that pattern to answer the last question. This is going to be written again right in the next one, so we can see it a few more times, and then we can start just using it as our pattern. Starting value multiplied by 1 plus the growth rate raised to the exponent. All right, so we're going to apply that to one more question. Okay, according to the 1991 census, the region of Niagara, Ontario had 364,552 residents. For the next few years, the population grew at a rate of 2.2% per year. For planning purposes, the regional government needs to determine the population of the region in the year 2010. So this is obviously an older question, but that's okay. We can still set it up and answer it, pretending that it's not 2010 yet. The algebraic model for this case is going to follow the pattern that we just saw on the last slide, and we're going to figure out what are the values that are going to go in each of these spots, and then answer a question. So what is the initial population? P naught, 364,552. The growth rate is 2.2%, but we need to change it to its decimal form, so we can divide by 100 to get 0.022, which is the decimal form of that same number. How many growth periods are there? This one, we need to do a tiny bit of thinking. So I'm going to do this one maybe down below. How many growth periods? We're growing by 2.2% per year, but how many years? So we're going to figure out how much time has passed between 2010 and 1991 by subtracting those two numbers. we can find out that that has been 19 years. All right, so our population is going to grow 19 times. Write the algebraic model for this situation. So it's going to use that structure given in the question. Population after n growth periods is going to be the initial amount, 364,552, multiplied by 1 plus the interest rate, raised to the exponent n. This bracket, it is totally accurate, and it shows you that you're starting with your initial population and you're adding some growth amount to it. So this is great, but if you'd like to, you can write that a little bit more efficiently by like right away adding those two things together and skipping that first step. So I would be okay with seeing this as your formula. So you can pick which of those versions you like better. And then finally, use the model for part E. Use that model or that formula to find the population in the year 2010, which we now know is 19 growth periods later. So the population after 19 growth periods, we can replace the n in the formula with 19. And again, this is going to need for sure a calculator to help us with an answer. I'd like to type in, whoops, that got messy. I like to type in the exponent part first. And then multiply by the number in front. I'm just going to include the final answer here, 551,222. And for a proper problem solving question, we would include a therefore statement. So I'm kind of out of space, but I'll include something up here. Therefore, in 2010, the population should be 551,222. Alrighty, so that's it for exponential growth. I'm going to stop this video here and then start a new one for exponential decay, which is a separate handout.